Good afternoon. We're right at 12:30. We have a few folks that we are still waiting to get in, trying to get in from the lobby. So give us about another minute or two, and then we will get started. Good afternoon. Welcome, everyone. We have a few folks who are still trickling in from the lobby, but we're going to go ahead and get started. So welcome to this webinar about the Green Infrastructure Toolkit for Texas communities. I am Charis York, the program lead for the Green Infrastructure for Texas team. We are part of the Texas A&M AgriLife Extension Service Disaster Assessment and Recovery Unit Mitigation Branch. A few housekeeping notes. This webinar is being recorded, and we will make it available in the next week or so. We also have a chat that is open for you guys. And we'll be sharing some links and not registrations, resources in there during the presentations. We also have a Q&A box that is open. So if you have questions that you think of during the course of the presentations, feel free to go ahead and drop them into that Q&A box, and we will have a dedicated time at the end of the session to answer those. We have a couple of speakers today. This toolkit is funded by the Texas General Land Office and is created in partnership with Fraser Nichols Incorporated. So today you will hear from myself, my coworker, Michael Niebuhr with Extension, and also Sheena Providence, Allison Hand, and Kim Potok from Fraser Nichols. So with that, we are going to go ahead and get started. Can you advance the slide? Excellent. So what are we going to cover today? We're going to start out with a little bit of background information about water in Texas and about the GIFT program and green infrastructure. And then we will take a deep dive into the toolkit, how it's arranged, what's included, and how you all can use it in your work. Like I mentioned before, we'll end with questions and answers, so feel free to put those in the Q&A box as we go along. And we might actually tackle some of those in the chat depending on if we can drop a resource or something like that as we go, but we will have questions and answers at the end. So let's get started. Next. And next. There we go. So it feels like we are always talking about water in Texas. Is there too much? Is there not enough? And the Texas Water Development Board was tasked with the state legislature to create the first flood plan for the state of Texas, which they put out in 2024. It's intended to be updated every 5 years and includes lists of projects that can be undertaken to reduce the flood risk for Texas residents. So the map on this page is from that flood plan. Towards the coast, you can see some of the dark pink areas that are considered to be flood-prone areas. But hopefully, and I think what you probably notice more is the blue areas that are dispersed across the state. And these are the flood hazard areas. So basically, we see flooding everywhere in Texas, and this map does not necessarily account for localized flooding that we see related to stormwater. So no matter where you're located, in the last 10 years, you have probably experienced or been very close to somewhere that experienced flooding. No matter where you live, you are not safe from flooding. One of the best ways to protect our communities from flooding is to leave space for water. That can look a lot of different ways, and green infrastructure or nature-based solutions are some of the best tools that we have to make space or leave space for water. Next. So the Water Development Board also writes the state water plan that's updated every 5 years. So the 2022 plan is the most uh, recent iteration of this. It also has a list of projects across the state, but its focus is primarily on drinking water. But we all know that water is water, right? The water that we're drinking one day is the same water that's flooding someone else the next day. We tend to think about water in different categories: stormwater, drinking water, flood water, but really they are all connected. So if you look at table 6.1 at the bottom of this slide, it is the projected annual water needs for the state of Texas over the next 50 years, and it's broken down into category. So I want to draw your attention especially to the last column where we're looking at the percent change. So that's how much additional we expected to need. And you will see that the biggest increase is in the municipal category, expecting a 1,300% increase in the needed amount of water. And the only area where we see a decrease is in the category of mining. So creating more water is really, really expensive. There's a huge opportunity for water conservation, especially with our outdoor water usage. How often do we sink a large amount of resources into creating clean drinking water that we then just dump onto the ground? Now, that might sound a little extreme, but if you think about it, isn't that what we're doing with our irrigation systems? We're cleaning that water to a point where we can drink it, and then we're pouring it on the ground. If we're using our potable water for irrigation. So practices like collecting and using rainwater for irrigation or non-potable uses, choosing a native and adapted vegetation that require less irrigation, and generally thinking about our water supply and consumption more holistically are all ways to reduce the need for that potable water and to think about the water all collectively. So are we expecting our projects to address all aspects of water quantity? And if not, why not? So next. So the last aspects of water that I want to talk about is our surface water quality. In Texas, it is the Texas Commission on Environmental Quality and the Texas State Soil and Water Conservation Board who are tasked with monitoring the quality of our surface waters. So that means our rivers, our creeks, our lakes, our bayous. This map is from the TCEQ website. It's the Surface Water Quality Viewer. It's a GIS tool that's available that anyone can access. And what we're looking at right now is just a map of the surface waters in Texas. So it shows kind of what you would expect. A lot of Texas and a lot of water in East Texas, not so much water in West Texas. But because it is a GIS tool, you can turn on and off different layers and look at different aspects of the map. So next. So this map with the red lines, now we're looking at the impaired water bodies. So this means that according to the state of Texas, these bodies of water do not meet their water quality standard for their intended use. That could mean that they have high levels of fecal coliform bacteria, low levels of dissolved oxygen. They could have issues with nutrients or total suspended solids or other contaminants. In Texas, more than 50% of the impaired water bodies have high levels of fecal coliform bacteria. There are a lot of groups across the state who are working on plans and efforts to improve our surface water quality, and most of those groups have identified green infrastructure practices that filter runoff as a way to improve water quality. So that is kind of a crash course in our water issues next across Texas. There's more that we could talk about, but I want to make sure we can get into the toolkit. So I'm going to give you just a little bit more background information before we move on. Just a couple more slides. Next. So I mentioned that we are part of the mitigation side of the Disaster Assessment and Recovery Unit of the Texas A&M AgriLife Extension Service. So the GIF team and Extension exists to be an educational resource and a connection between the university and the public. So to bring research-based information to Texans in a way that is accessible and useful. So the GIF team We do that through educational events like this workshop, this webinar, through workshops and field days. We also work directly with communities to help get projects on the ground. And finally, we do applied research, especially looking at green infrastructure practices that have been installed, evaluating them and making sure that we continue to recommend the best practices and approaches that work here in Texas. Next. So we also talk about green infrastructure at different scales. So maybe a practice that works for an individual home or business, practices that are best suited for maybe a whole neighborhood or a small community, all the way up to the large-scale protection, preservation, and restoration of our natural areas for the ecosystem services that those provide to us. So the toolkit that we are talking about today focuses primarily on practices in the site scale and the mid-scale range. If you're interested in some of those larger scale practices, we do have resources on our website about those, and we encourage you to go check those out. So that is a little bit about the GIFT team. And now I'm going to hand it over to our next presenter, Michael Niebuhr.
All right, thanks, Sharis. Howdy, guys. Before we dive in, I want to briefly acknowledge the different terms you may have heard in the past, you may hear during this presentation that reference green infrastructure. Phrases like nature-based solutions, low-impact development, green infrastructure, green stormwater infrastructure, you might even hear blue-green infrastructure or stormwater retrofits. While each of these terms might have a slightly different context when it comes to, say, planning or engineering or policy, they're all describing basically the same thing. At the core of it is using nature inspired systems to manage that stormwater, reduce flooding, and to improve water quality and provide those community environmental benefits. So for the purpose of today's discussion, let's not get hung up on terminology. Let's use these terms somewhat interchangeably. And when we say green infrastructure today, we're generally referring to this whole family of practices. So it's not about the label, really. It's more about the approach, function, and how they can be applied effectively in your community. So next slide. So green infrastructure delivers multiple benefits that go far beyond just managing that stormwater. So obviously that's a big aspect of it. It standards that stormwater naturally, slowing runoff, reducing volume, relieving pressure on your drainage systems. And these practices are flexible. They can be easy to install. I mean, they can fit into your already existing community, your streets, parking lots, and neighborhoods. Secondly, it builds resilience. Green infrastructure can lower long-term operations and maintenance costs. It often aligns well with funding and permitting programs that are now starting to prioritize those nature-based solutions. Third, it can enhance community space, can create that visible public benefits and improving the aesthetics through greener, more usable and more multi-purpose spaces. And finally, it can support long-term sustainability by improving water quality, promoting groundwater recharge, and providing habitat for wildlife, helping communities adapt while protecting the natural systems. Next slide. So this project came out of the results from the flooding during Hurricane Harvey. And while much of the focus is related to coastal region impacted by that flooding, the goal is that this toolkit can be used statewide as these individual practices allow. So the goal of our project was to empower Texas coastal communities to plan, design, and implement green infrastructure that enhances their resilience and sustainability. And so we do that with this user-friendly workflow toolkit to guide communities in selecting and integrating those GI practices. It contains multiple design sets detailing siting, design, vegetation, and maintenance. The good thing about this does align with Texas Water Development Board's nature-based solutions for flood resilience manual that will be coming out this year. And as always, here at AgriLife, we want to provide that education. So we're here to provide the background for maybe presentations or workshops or other information about this toolkit to help your community. Next slide. And so remember, this is more than just design. It's a process that connects the science, the planning, and the practice. So it provides a step-by-step framework for stakeholders. When we think of that as practitioners, decision makers, your developers, to apply these green infrastructure practices. It helps your team select the right practice for the right place, balancing infiltration, filtration, and site constraints. Promotes collaboration among engineers, planners, ecologists to ensure resilient and maintainable designs, and to translate policy and technical standards into actionable tools for project delivery and permitting. So I'd like to pass this along, the remainder of the webinar, over to our team at Freeze and Nichols, and they're going to walk us through the toolkit, focusing primarily on how to use this toolkit to fulfill your community's needs. So Sheena, you guys at Freeze and Nichols, please take it away.
Yeah, thanks, Michael. So I'll start off with the implementation guide, which is essentially your starting point and pretty much the first step to review before diving into any design set. And so within this implementation guide, you'll see it outlines, the workflow from site assessment to design, maintenance, funding guidance, incentives, regulations, and really the intention of the implementation guide is to ensure that every green infrastructure project starts with the right approach. And so it's important to reference this throughout the entire process and not just at the beginning. So kind of the first step is really understanding your project team. On the right, you can see an exact screenshot of kind of the first page of the implementation guide when you open it up. And so as Michael and Charis both mentioned, green infrastructure is inherently multidisciplinary. And so as a result, it requires multidisciplinary teams, including engineers, landscape architects, hydrologists, planners, maintenance staff, contractors, the list goes on. And so really the intent there is that each discipline or expert kind of provides their own unique perspective when it comes to building these multifunctional and multi-beneficial resilient systems. And it's also important to note that including maintenance staff early on in the design really does help ensure that long-term functionality and the ability to maintain these systems over time. And I also want to bring attention to stakeholder engagement. This is really critical, whether it's through local officials, residents, developers, nonprofit organizations. It's really important to kind of build that trust to ensure that these green infrastructure projects align with community priorities. You can get to the next slide. And so after kind of introducing some of that introductory material, the guide then goes kind of step by step at a high level, kind of an overview of the preliminary kind of design process. And so that first step is the preliminary site assessment, which within this step, you really want to identify the conditions and constraints that will influence design and construction. And so this step isn't necessarily drastically different from your typical gray infrastructure projects, but I'll walk you through an example in which it might be a little bit different from a green infrastructure perspective. And so when you're looking at the different conditions and constraints, you're identifying your drainage areas, soils, slopes, downstream infrastructure, utilities. And the example of kind of GI specific practices and implementation for soils, for example, you may want to perform soil testing to identify infiltration capacity. And if it's not to the standard that you need for a given practice, you have to adapt as needed. And so some of those adaptation requirements may consider, adding structural features like under drains for areas where you may have low permeability soils, or even incorporating amendments to improve the overall performance. And then to kind of tag team onto that, in the example of utilities, it's important to understand the existing utilities, space limitations, and access constraints to resolve any of these issues early on in the process and to avoid, potentially costly delays later on in design. So the next step is really understanding the difference between infiltration and filtration-based systems. And so I'll kind of flip what we're seeing on the screen here. We're going to start with the infiltration-based kind of definition. And so infiltration-based systems are meant to manage stormwater by allowing it to soak into the ground. And so a lot of these practices, such as, rain gardens, bioretention, bioswales, infiltration trenches, have similar functions and use pollutant removal mechanisms to pretty much improve water quality runoff and promote groundwater recharge. However, these systems can easily become filtration based if the permeability isn't great. And so filtration based systems typically focus on capturing, storing, and treating stormwater through detention or reuse. And each type, you know, offers treatment functions that complement or substitute the infiltration based practices where soil conditions, groundwater levels, or other site constraints may limit feasibility. And so on the right hand side here, you can see again an exact screenshot of what this looks like in the implementation guide itself. It's kind of, again, meant to be a high level kind of matrix that shows you the different common applications, whether you're looking at a residential, commercial, or industrial site, if you're looking at an area that may have limited space, or parks, or even areas with high traffic or low traffic roadways. And so this kind of matrix here is meant to just show you at a high level kind of the common applications for each, filtration or infiltration based systems in their contributing drainage areas and how they could, be applied. So next, we need to determine the water quality volume to be treated. And so once the preliminary site assessment is complete, we have to, size the GI practice accordingly to capture and treat that volume. And so looking at kind of this equation on the left-hand side of the screen, we have water quality volume is equal to the C value, which is the runoff coefficient, multiplied by the rainfall depth, and then multiply that by the area. And so it's important to note to be mindful of when you're using this guide, to be mindful of the unit conversions. And so rainfall depth is in inches, so it's divided by 12 to convert that to feet. But area, for example, here is in square feet, where typically we're looking at area in acres. So just kind of small things like that. Be mindful of that you're doing those unit conversions as you're going through the guide itself. And I also want to note that the rainfall depth, the P value here, should be based on local regulations, but if no standard exists, typically a minimum 1 inch rainfall depth is recommended. And so it's also important to ensure that after you determine this water quality volume, that you want to ensure that your system can also safely pass, larger design storms. Next, we want to understand the different sizing requirements. And so proper system sizing is really critical for ensuring functionality, efficiency, and maximizing pollutant removal. And so on the right-hand side of the screen here, you can see kind of the detailed typical design and sizing criteria for all of the different GI practices within the toolkit itself. And so again, this table is meant as kind of a cursory high-level overview of, just kind of to help you narrow down the options to inform the GI selection kind of type up front. And so you'll find, the maximum drainage area, maximum contributing drainage area within this table, ponding depth, media depth, minimum infiltration rates, as well as drawdown times and other sizing criteria. And you can switch to the next slide here. And so after we understand the system sizing, the next step is landscape design. And so you really want to carefully consider the soil and vegetation because they directly impact performance and the durability of a system, since soil media is typically the primary treatment mechanism within these vegetated green infrastructure systems. And so this is another example of just kind of those multidisciplinary teams in action, because landscape design is typically done by landscape architects as well as those environmental scientists. So you really want to lean on them and their expertise as much as possible, because they are typically the experts that understand, the materials, the soil blends, the typical mixtures needed to kind of sustain these types of systems. And so I want to call some attention to, again, the screenshot on the right-hand side, taken directly from the implementation guide itself. You can see, looking at the typical blend, it may be between 70 to 80% concrete sand, 20 to 30% clay, 10 to 15% 20 to 30% screened bulk topsoil. And then within that, the mixture should have, 70 to 90% sand and coarse fragments, 3 to 10% clay, less than 20% silt, and then 0.5 to 5% organic matter. And so organic matter is necessary, but it also has to be carefully limited and specified. And so excess organic matter can pose water quality risks, especially as it relates to nutrients. And so high compost content can typically leach total phosphorus or TP during storm events, which ultimately, instead of treating runoff, leads to poorly designed media that can increase pollutant loading. And so kind of the key takeaway here is that you really want to make sure you have the correct and proper media selection, and that soil testing takes place to ensure that you're achieving the water quality goals that you want for your given GI practice. And then to continue with landscape design here, we also kind of developed this vegetation matrix. And so this table 4 is really just a preview of the different vegetative species. And you'll notice that it says specific to the Gulf prairies and marshes region. So again, highlighting that this project was funded, from disaster relief funding from Hurricane Harvey, which is why this table and some of the language within the implementation guide and the toolkit itself is specific to coastal. But again, the intent is to be able to use this as much as possible in non-coastal areas as well. And there are plenty of resources out there if your, project area isn't in a coastal region. And so really, the story here is that effective vegetative species selection for green infrastructure should be informed by, your own regional planting guidance, expert input from landscape architects and ecological professionals, as well as a thorough understanding of, the local ecoregions and site-specific conditions. And just kind of looking through this table, again, pretty high level, you'll notice that the vegetative types that are highlighted within this matrix are wildflowers, grasses, vines, trees, and shrubs. So there's variety and diversity within kind of your vegetative species there, as well as the different plant characteristics and tolerances, whether that's longevity, is it annual, perennial, biennial? Does it benefit pollinators? What is some of the aesthetic features like the bloom color, as well as the plant height? And then kind of from a flood mitigation, water quality perspective, the different condition tolerances, whether that's flood, salt, or drought. And I also want to note that all of these different categories are defined in great detail within the implementation guide itself. So next, it's important to understand, construction, the general construction process to ensure, excavation, component installation, and vegetation establishment are properly executed so that the system functions as it's intended. And so again, this is a screenshot from the implementation guide itself. So there are actually 6 steps, but here is only pictured. Here we only have 4 of those pictured just from a spatial perspective. And so I'll kind of run through that list. Step 1 is pre-construction prep. Step 2, excavation. 3, installing the green infrastructure components themselves. 4 is verifying quality control. And then 5, which is not pictured, vegetation. And then 6, oversight and inspections. And so the way in which this section for construction was built is kind of like a checklist. So that way it makes it as kind of digestible as possible as you're going through this process. And so in the example of pre-construction prep, what do some of those tasks potentially look like? That could look like installing temporary erosion and sediment controls, staking the site, and clearly marking utilities, ensuring that runoff is routed around the green infrastructure practice until the site is fully stabilized. And just kind of funny story here for this particular project, San Gabriel Parkway. One lesson learned here is, the engineer and the consultant had to walk the contractor through this design, like physically hold their hand and walk them through this design because oftentimes the contractors that are put on these types of projects don't really understand the, design intent of these systems and how they're meant to function. And so I believe the engineer had to kind of mark here, if you can see that curb cut kind of in the middle of the screen, They had to physically stand there and say like, hey, like this is exactly where the location of where this curb cut needs to happen so that the system can function as intended and water can enter the system as we intended. So just important things to kind of keep in mind during that construction process. Another important component to consider upfront before implementing any green infrastructure practice is coordination with the various agencies. And so that can look like the local, state, or federal agencies. And so at the local level, that may look like coordinating with any agency that manages drainage systems and waterways to identify design and construction requirements and to confirm applicable drainage, transportation, building codes, zoning codes, and those you can typically check your city's public works, engineering, and or like planning website for that information. At the state level here in Texas, that'll likely look like coordination with GLO for sites near coastal and or sensitive water resources, the Water Development Board for technical guidance, planning resources, funding programs for water-related infrastructure, or even TCEQ from a stormwater pollution prevention plan perspective, of course, which is dependent on your project size. And then lastly, at the federal level, that could look like coordination with FEMA if a project is within a map plane. So step 8, we have operations and maintenance, which is arguably the most critical piece of the puzzle for green infrastructure to ensure that functionality, sustainability, and resilience, actually last. And so it's really the kind of key messaging here is that it's important to establish a mutually agreed upon O&M plan for the long-term success of these practices. And so within that plan, you should clearly define, various maintenance responsibilities, inspection schedules, and different performance goals. It also outlines some of those routine tasks, such as, removing debris, inspections of different structural features, or even kind of clearing trash racks. One other important note from an O&M perspective is that educational signage really does go a long way. It not only brings that awareness, but again, it increases kind of public education and knowledge, as well as almost like community ownership and responsibility and stewardship towards wanting to help maintain these systems. And you'll see within the individual design sets, they have their own individual kind of O&M matrix, if you will. And, when Kim and Allison present in a little bit, you will see some of those examples. There's also an entire section in the implementation guide that includes regulations, hindrances, and incentives to help essentially with a smoother project delivery. And so it's important to note too that this isn't just based on, individual feedback in Texas or for this project. This is kind of stakeholder industry-wide feedback for general concerns and barriers that we've seen kind of nationwide for getting these projects in the ground. And so this section is really intended to highlight the uncertainty in permitting and the approval processes as a major barrier, but it also, focuses on the unique challenges specific to Texas, which may include, limited local resources and or complex permitting. And despite kind of these barriers, it also highlights some of the different incentive programs that are available, such as stormwater discount fees, development incentives, grants, rebates and financing, and installation financing, as well as award and recognition programs. And lastly, at the end of the implementation guide, there's an entire section dedicated towards, different funding tools and resources to help bridge the gap between planning and implementation of these types of practices. And so green infrastructure is very unique and niche in the sense that it often draws on a mix of funding resources because of its multiple benefits, whether that's, from a stormwater management perspective, from a flood mitigation perspective, habitat, mental health, community livability, the list kind of goes on. And so within this section, you'll find that each source, has its own timeline, their own requirements, and the availability of funds. And there's 3 different funding tools that we've outlined within the guide itself. We have a table dedicated to local public revenue, a table dedicated to different partnership sources, and then a table dedicated to state and federal funding. And so it really just is meant to kind of highlight the opportunities to kind of collaborate with nonprofits, academic institutions such as, Clean Coast Texas, as well as a compiled list of just the available programs and grants that support GI from a planning, design, and construction perspective. And so after going through the implementation guide, you'll notice that within all of the design sets, we kind of have these 6 different key topics. We have applications and siting, the different B&P specific considerations, challenges, and limitations, the design elements for a given GI practice, their step-by-step instructions and calculations of how to actually design and size these systems, permitting, construction, and maintenance considerations, as well as kind of your typical standard CAD detail. And with that, I'll pass this off to Allison, who would touch on filtration-based systems.
Thank you, Sheena. So now we're going to walk through now that we have walked through how to use the implementation guide, we're going to walk through how to use the filtration-based systems design sets. So as a reminder, filtration-based green infrastructure focuses on capturing and storing and treating stormwater through detention or reuse, often with structural components like pumps, outfall structures, and the like. So we created 3 filtration-based design sets: rainwater harvesting, wet ponds, and constructed wetlands. Next, we'll briefly discuss rainwater harvesting and constructed wetlands, and then we'll go step by step through the wet pond design set. So rainwater harvesting is a green infrastructure approach that doubles as a water supply approach, in which rainwater is collected from roofs and other impervious surfaces, diverted, and stored for later use, instead of becoming runoff to the local drainage system. These systems are often versatile and can be designed for any site with any land use. The design of your cistern depends on your project goals. For example, if water reuse is the goal, a leaf screen and first flush diverter can remove debris, rust, dust, and contaminants from the system before runoff enters the cistern. But if water quality and water storage are goals of your project, you might want to consider avoiding diverting the first flush to capture those pollutants in the cistern instead of sending them into the local drainage system. State law here in Texas prevents HOAs from prohibiting rainwater harvesting systems, but some don't want to see it. So make sure you check your local ordinances if they have any guidelines regarding the placement or visibility that you need to follow while designing these systems. Without local regulations, the design set provides recommendations for siting, sizing, and maintenance. And then for the rainwater harvesting system specifically, these can be designed above ground or below ground using our design sets. Next, for constructed wetlands. Constructed wetlands are shallow vegetated basins designed to mimic natural wetland systems for the purpose of treating stormwater runoff. These systems use a combination of sedimentation, plant uptake, and microbial activity to remove pollutants from runoff. In addition to their primary water quality function, constructed wetlands can provide wildlife habitat, reduce flood peak flows, and offer aesthetic and recreational values in urban landscapes. While constructed wetlands work best when designed to serve a smaller contributing area, multiple cells can be designed to work together for larger areas. The constructed wetland design set provides considerations and recommendations to common challenges such as how to prevent mosquitoes from breathing in shallow waters, nobody wants that, how to prevent algae blooms, and how to handle sedimentation accumulation to maximize vegetation treatment and efficiency. Okay, so a wet pond is where we'll dive deeper. A wet pond is a type of engineered basin used to treat and retain stormwater runoff, providing multiple benefits related to flood mitigation, water quality improvement, and ecosystem support. By maintaining a permanent pool of water, wet ponds improve water quality by allowing sediment to settle out of the water. Using additional detention volume stacked on top of the permanent pool, wet ponds reduce and delay peak flows to mitigate flooding. Constructed wetland cells are often design components of a wetland around its fringes. Diving deeper, wet ponds can serve the largest contributing area of any of the green infrastructure practices we'll talk about today. They can be designed new or in some cases, an existing detention pond can be retrofitted into a wet pond. Compared to traditional dry bottom detention ponds, wet ponds are an amenity to the community. Now, I'll add a wet pond is more than a retention basin with a fountain. There are more specific natural design components to a wet pond. The drainage patterns of the existing and your proposed site should be considered when selecting the location of a wet pond to receive runoff. In many cases, storm drains can be directed to the wet pond to receive that runoff. As with constructed wetlands, your base flow or makeup water is needed to maintain that permanent pool. The design set walks through the decisions of including a liner, depending on groundwater conditions. This is not meant for infiltration. That Kim will talk about infiltration in a little bit. Our goal is not infiltration, and if your groundwater table is too high, often you need a liner to prevent interaction between your permanent pool and the groundwater table. In summary, the overall design is focused on providing flood storage while allowing for pollutant settling. The goal of a wet pond, like I said, is not infiltration. It's to store and slowly release after your peak those flood flows. Okay. The design set begins with some common challenges designers face when designing wet ponds and an explanation of how the design set can help overcome each challenge. For example, sustaining the permanent pool during long, hot summer months where rainfall can't keep up with evaporation is a challenge the designers face. Well, designing your wet pond with a source of makeup water can help overcome this challenge. In some projects, your rainwater harvesting may be a source of makeup water. Very, very important. Your makeup water cannot be chlorinated. So using potable water is not sustainable. But also if you're using chlorinated water, it will create issues with your vegetation. So make sure whatever makeup water you use is not chlorinated. Just as with constructed wetlands, controlling your algae bloom is important for wet pond design, maintenance, and overall aesthetics. Aeration may be the solution, but you may be able to select different plants that have a higher nutrient removal capacity as your solution. So this is where the back and forth goes with the implementation guide for some of these decisions that apply across different green infrastructure practices. Like I mentioned earlier, wet ponds are the largest green infrastructure practices we'll talk about today. As a result, there are more than a few design elements. The design set walks designers through best practices for designing inlets, outlets, your pond geometry, selecting your vegetation, and much more. One thing that I'll highlight here on our design elements is the public as an element of a wet pond's design. As an engineer, the people element of a design often creates the most uncertainty. Public stakeholder engagement is key to successful implementation. While you know the great benefits of your new wet pond, someone from the public might complain that it's overgrown and not maintained. So best practices for stakeholder engagement include incorporating educational signage to teach them what is going on, incorporating walking paths and bridges and naturalized landscape to improve public acceptance, prohibiting swimming or taking a fish using signage, as well as with most detention ponds, we want to include a safety bench around the perimeter for physical safety of the public. Okay, each design set includes a standard detail for reference. These details should not be used for construction drawings, but can be used as a go-by when drafting your own details. They also help to provide a visual reference of the different design elements that we'll be talking about. So next, we'll walk through the 6 design steps to calculate relevant values and complete balance checks within your wet pond design. So starting off, number 1, the permanent pool in your wet pond holds and treats the water quality volume. This is the lowest level of your wet pond where most of the treatment occurs. Runoff displaces the water in the permanent pool during each storm event, and the permanent pool should remain mostly full at all times to keep the wetland plants alive and dissipate energy from inflows. So step 1, how big does your pond need to be? Your permanent pool volume should equal the water quality volume you want to treat. Like Sheena mentioned, you need to check your local drainage regulations, but but if no standards exist, the implementation guide is there to help. So your permanent pool volume is equal to your water quality volume. So next up, we need to determine the sediment forebay, the main pool, and the extended detention volume. First stop for entering the wet pond is the sediment forebay. A sediment forebay should be included at each inlet to ensure sediment and large debris are removed before entering the main pool. After the sediment forebay, runoff enters the main pool. The extended detention volume is located above the permanent pool and is contained within the berms of the pond. The extended detention pool provides temporary storage during storm events and functions to minimize turbulence by decreasing pond flow through rate and enhances sedimentation. This above your permanent pool functions much like a traditional detention pond, but you really get the water quality benefits of a wet pond below your permanent pool volume. After the storm ends, the extended detention pool draws down over a period of 48 or 72 hours, depending on your primary goal of the pond. If your goal is flood control versus water quality, you might want to hold the water a little bit longer, depending on the flow patterns of the surrounding area. Okay. So your permanent pool volume is made up of your sediment forebay and your main pool volume. The sediment forebay volume should be a minimum of 20% of the total permanent pool volume, and the main pool will make up the remainder. Above the permanent pool, like I said, is the extended detention volume. This should be a minimum of 50% of the permanent pool volume to maintain balance. So walking through together with some very round numbers, if your permanent pool volume is equal to 100 cubic feet, then your sediment forebay volume should be about 20 cubic feet, your main pool about 80, and then your extended detention volume about 50. This could be much larger depending on your project goals and how much flood storage you need to provide. Once you've set your volume goals, next decision is the geometry. The design set provides recommended minimum and maximum values for each design decision. Over the next few slides, we'll walk through some of these design decisions. First off, the main pool should be designed with an irregular shape to improve aesthetics and mimic natural wetlands. We're not fooling any birds with a square rectangular pond. We want these systems to look more natural to mimic the natural habitats. The main pool depth should be between 6 to 8 feet deep. It can't be any deeper to avoid anaerobic and odorous conditions, and we wouldn't recommend going shallower to avoid murky pond coloring. Okay, so permanent pool, 6 to 8 feet. Quickly, other design decisions. The minimum slope should be 2 to 1 from inlet to outlet. This helps to maximize pollutant removal and avoid shortcutting the water treatment functions. If the water's getting out too quickly, then it's not being treated. Good practice for earthen side slopes is to be no steeper than 3 to 1. And with the extended detention pool, the pond should include a safety bench. The design set suggests a 15 to 1 slope, but your local drainage regulations might recommend something different. Okay. So we've been talking a lot about the permanent pool and the sediment forebay, but how do those connect? The interbasin separator berm separates the sediment forebay from the main pool. As shown as with my arrow, the berm should be minimum 2 feet on top and should be set at least 2 feet below your permanent pool elevation. The interbasin pipe, shown as F on our detail, hydraulically connects the sediment forebay and the main pool through a submerged pipe portal to promote aquatic water supply during dry conditions. The elevation of the interbasin pipe should be 2 feet above the bottom of the forebay, and a plug valve should be included to allow for independent draining by pump of the sediment forebay for maintenance. So to reiterate, the design set discusses these recommendations and many more for developing your pond geometry. The design of the outfall pump is important to enhance the detention function of the pond. In most cases, the ponds will be designed with two primary outfall structures and a maintenance drain. First, the extended detention orifice, highlighted in yellow, typically is a PVC pipe. The outfall should discharge to a manhole if you're connecting to a downstream storm sewer system. Walking through some things to consider when designing your extended detention orifice. Your inlet invert should be about 50% of the permanent pool depth, and your outlet should be set at your permanent pool elevation. So drawdown time of the extended detention volume should be at least 48 hours to allow for sedimentation. If the pond drains too quickly, then it won't achieve the intended water quality function. Note for the size of the pipe should be no smaller than it can be maintained. If you need a smaller pipe than your maintenance crews want to clean out, you may need to use an orifice slide as a restrictor to achieve the detention and drawdown goals. The design set provides formulas to calculate your outlet size. Here you can see the orifice flow equation, but if an orifice plate is not used to control the drawdown, the flow in different equation will be used to make sure that we're fully capturing the energy loss of that orifice. Okay. The second element of the outlet structure is the overflow spillway. The spillway sits above the extended detention pool and controls your discharge. The overflow spillway typically consists of a riser structure that may contain multiple openings at different levels, or can consist of a series of one or more weirs along the embankment. Your local drainage criteria should control the design of the spillway, but if there are no regulations, the design set recommends the spillway be designed to safely pass the 100-year storm. And for the spillway, the weir equation should be used for sizing when you're using weir. So wetland plantings provide both function and aesthetic to your wet pond. Vegetation should account for your moisture zones. Where are you planting different types of vegetation should depend on your permanent pool elevation. The figure on the screen from the City of Austin Environmental Criteria Manual shows the edge, marsh, and deep water zones relative to your permanent pool elevation. Reference the implementation guide before selecting vegetation for each zone. Make sure you coordinate with your landscape architect, and most importantly, avoid invasive species in your design. Okay. You can determine the quantity of plants needed based on the area of the permanent pool. We recommend 3% of the area in square feet as a good estimate for the number of plantings to include. Additional source of water, your makeup water, is typically required to maintain your permanent pool. A water balance determines the amount of makeup water that would be required, if any is required, for your system. Inflows to the pond include your direct rainfall and runoff from your contributing watershed, while outflows include evapotranspiration, seepage, and any water drawn from the pond for, maybe irrigation. Harris County Flood Control District and the City of Austin both have good guidance on performing water quality balances. We recommend checking those references when you're completing this step. If any changes are made to your pond geometry once you perform your water quality balance, you need to complete the water quality balance to make sure that the final design is fully balanced with the project goals. And again, reiterating, when we're talking about makeup water, this cannot be chlorinated. Often people use groundwater wells or more sustainably a rainwater harvesting system from a nearby rooftop. To wrap up our discussions on wet ponds, the design set provides detailed recommendations and considerations for permitting, construction, and maintenance. Each design set includes suggested regular and as-needed maintenance activities. Best practices for green infrastructure maintenance plans is to be specific when defining triggers for, quote, as-needed maintenance. As needed is not very helpful to your maintenance crew. They need to know when. For example, you should check your sediment levels in the forebay every 3 years. Just generally saying every few years or as needed is not as helpful to your maintenance team as every 3 years. Check this. Or after a storm of at least 3 inches of rainfall, check these items. And then for those who are in a coastal area, you may have a shallow water table, tidal influence, or high salinity levels on your site. The design set provides considerations to adapt your design to be more resilient and still effective under these conditions. And with that, I'll hand it off to Kim Patok to talk about our infiltration-based system design sets.
Thank you, Allison. So the infiltration-based systems vary from the filtration systems that Allison detailed because they're designed to naturally allow the water, the stormwater runoff, to infiltrate into the ground to mimic natural design processes. But depending on your infiltration conditions of your site, these could very easily become filtration systems if your site conditions do not allow much infiltration. So completely dependent on your infiltration testing to be done early in the job site to identify the type of control and the type of mechanisms you'll need. Next slide. So in the toolkit, we've included design sets for 4 different types of infiltration-based systems. These are the most commonly used in the industry, and really wanted to make sure that we're kind of covering the full spectrum of small site scale BMPs like a rain garden up through a larger contributing area BMP of a bioretention basin. And then depending on how things work, they, for various land use types as well, and then for varying infiltration conditions as well. Next. We're also going to we're going to detail a little bit on each of the design sets, but to spend the most of the time talking about the design of a bioretention basin. So for a rain garden in itself, this is considered more of a small site scale type of BMP. And we've got for a smaller contributing drainage area, and really can be used really in small contributing drainage areas along a sidewalk or along a curb line in somebody's backyard at the end of a downspout, really just depending on what type of water quality goals you have in the area that you have. But they're really considered just small, dry areas to really trap debris and pollutants from small storms. They're easy to implement along a block side or a parking lot and customizable to the geometry of your site conditions. Also, depending on what you're wanting your planting palette to look like, they could be easily planted just with sod if you really don't want to have much maintenance to the site, or really densely planted to provide maybe a pollinator garden and an amenity for a neighborhood. So really just customizable to what really your maintenance needs are, but recognizing the fact that if you have more densely rooted, then you're going to get better pollutant uptake and better trapping of pollutants than rather if you were to have short sodded situation, because you just don't have that rooted species and the longer grass to really able to catch things as it moves through the system. The next one that we've included is a bioswale. Think of this as just your typical grassy swale along the side of the road or a vegetated median. But we are wanting to trap the water, and it's still flowing naturally through the system, but we end up replacing that typical media or that typical topsoil and subsurface soil with some better engineered media to be able to trap more pollutants and store more water. So think of it as, rather than doing a elevated vegetated median in the middle of a road or on the roadside swale, that you allow to maybe depress that vegetated median and allow the water to drain to that median and to capture it and to be able to treat that water at the source. So also it serves as a great way of reducing your irrigation needs of an area, because say you want to do some great landscaping in an area, but then you want to put in a irrigation system to keep that vegetation established. Well, in this way, we combine multiple benefits, right? We have our vegetated area, but then we also have the natural water flow coming in or water runoff coming in through each storm event to be able to provide hydration to the plantings. One of the other design sets that's kind of more, it's not really that common, but it's a great BMP would be an infiltration trench. This is really served best as along completely impervious cover areas where you have very minimal fine particulates, because really this is, think of it as just a big trough, or not even big, but just a trough that's filled with gravel or cobble, and where the water just gets trapped inside of that and then just naturally infiltrates if you've got good infiltration conditions, or if you have poor or even mediocre infiltration conditions, it can also include an underdrain as well. But basically, it's just the water just sheet flows across an area and off of a sidewalk or off of a parking lot into that infiltration trench. And sometimes if you don't have more of a sheet flow condition, but you still want to use an infiltration trench, you can also tie in a storm drain system, like a pipe outfall into the sidewall of the infiltration trench. And oftentimes though, for that, you really need to make sure that you've got an upstream control, like another kind of, maybe a rain garter or a detention pond or something, to be able to trap that debris upstream, because you really don't want those fine particulates and trash coming into the trench. And they're really going to take most of the time and the remaining time that we have today to talk about bioretention. So think of bioretention as a very large rain garden. So we talked a little bit about a rain garden, but bioretention is very similar, has similar components, but just is allowed to capture much larger contributing area. So it's more considered a regional control. So think of it as, if you're designing your site, that it's really more at the, all the runoff from the site would drain to this regional control, or like your entire storm drain system, or at least a component of the storm drain system, the main line would outfall into your bioretention system. It is a dry facility that is temporarily impounds water, just like a rain garden, and can be customizable for the design to meet your site's needs. And also even customizable for the vegetation practices, just like with a rain garden. If you want to just do it sod lined to be able to reduce maintenance, you can go for that, or it can be a beautiful amenity and a pollinator for a community if you were to do densely rooted and also add a tree canopy and such. But depending on your infiltration conditions, if you end up having to do an underdrain with the facility and you also want to install trees or bigger rooted species, you really need to think about that tree, the root zone, and how that we want to make sure that that does not impact the underdrain system. And one of the great amenities or features about a bioretention facility is it can be combined with a regular detention facility. Oftentimes, if you've got a regular detention need from your site because you have to mitigate flood runoff, you can stack the bioretention volume right on top. So you would have the flood detention on the bottom and the stacked bioretention on the top, or I'm sorry, just the opposite. Water quality on the bottom and flood detention on top. And you'll want to be able to allow that flood runoff, have a multi-stage riser in your facility and allow that the flood runoff to meet that still typical 24-hour drawdown, but the volume in the bottom that we're holding for the bioretention and the water quality improvements is you would want to hold it for a longer period of time, typically 48 hours, but no greater than 72 hours, to make sure you're not creating a mosquito nuisance. So we've highlighted a couple of the typical challenges that people have in implementing a bioretention facility. Like all infiltration designs, it's critical to perform infiltration testings during design and post-construction. So just you want to make sure that you safeguard that underdrain system, and even perch that underdrain system to allow natural infiltration, but continue to have an underdrain there just in case. But also it makes these type of BMPs make a great site amenity because of the landscaping plan. But it's important to communicate the purpose of the vegetation in public meetings and get that feedback from them, because they might want to have particular types of plantings in the facility, but just to really get that upfront feedback for them to understand their concerns and be able to address that during design. And like Allison mentioned, even in the wet pond design, the need for signage to educate folks on the purpose of the facility. Next slide. So a bioretention facility in general is considered a regional control because it's capable of treating up to a 10-acre watershed. But unlike rain gardens, where there are several along a block to treat small areas, these controls typically pick up an entire site or roadway and are placed at the end of a drainage system. But because their purpose is for water quality, it's important to maintain shallow sloped basins to settle out that runoff as it moves along. So if you have too steep of a basin, then your water is just going to pipe right through and it's just going to bypass the ability to settle out those pollutants. So it's important to meet the slope requirements that are outlined in the design set. But also, if the site has a shallow groundwater table, it might be important to include a liner. Also, if there's a hot spot in the area where you've got contaminants leaching up from the groundwater, that's a concern of the area. Including that liner is a possibility with the bioretention cell, but that obviously just require for you to do an under drain system because the water would have the inability to be able to drain and infiltrate naturally. Okay. So we've already touched on a couple of the elements with a design of a bioretention cell, but we've got a lot outlined in the design set, and I'm going to step through a lot of those just by using our schematic design details that are included in the design set. So one of the first one would be the way the water comes into the facility, and these are labeled as item A in the standard details. Click, please. So there are multiple ways that you can get water into a bioretention facility. Outlined here in the schematic drawing, this would be like a pipe outfall coming from, say, a parking lot, and then maybe, say, a downspout from a adjacent structure. But one of the most important things when you're looking at how the water is coming into your site is you want to put it at the very top end of your site so you have the longest flow path from your inlet to your outlet, but then also, go ahead and click, you want to make sure that you've got energy dissipation at each outlet. So you want to make sure that you're not propagating more sediment into your site or destabilizing an area. So you're dissipating that energy at each outlet, either maybe through a plunge pool or a splash pad in your site, depending on what type of flow and flow rates you're dealing with and velocities. Go ahead. When you take a look at where your flow is coming in, it's important to consider you really want at least the flow path to be 2 times as long as the width of your facility, because you really want to make that as long as possible to allow the biggest time for your pollutants to settle out. And you really want to make sure that that slope through that system is very shallow. So following the recommendations in the design set to make sure that you're able to have those pollutants settling out and just not having it as a bypass straight down to your outlet. The typical ponding depth of a bioretention cell really is up to the designer, is typically anywhere from 9 inches up to 18 inches to be able to draw down the adequate volume. But also click through. We also want to make sure that we've got a pre-treatment forebay to make sure that we don't have any kind of maintenance concerns, or you definitely will have maintenance concerns, but just to eliminate or to be able to minimize the sediment in the main pool area. Just similar to a wet pond, you want to trap those sediments and the larger debris in the pre-treatment forebay area. And then from there, you can start working on the main pool area. Typically, that pre-treatment volume is 20% of the water quality volume, just like in the design of a wet pond. And then depending on your site's infiltration, you'll want to do your infiltration testing of the subgrade material. So highlighted here in yellow at the bottom, that would just be your in situ material where you would want to do your infiltration testing. In the implementation guide, we provided a link to how to perform that infiltration testing. So it's important to follow that based on the size of your site, on how many test holes that you need. But like we've already mentioned, if doing that testing during the design, but also when we get to post-construction, either do testing formally, or you're going to need to fill your cell and monitor the drawdown rate to make sure that that drawdown time is met. So depending on your subsurface conditions will determine if you need to have an underdrain system. Your drawdown time should not exceed 72 hours because that would be considered beyond that, starting to become mosquito breeding season, or not season, but mosquito breeding opportunities. But that you also want to make sure that your drawdown time is no less than 48 hours, so you have maximum amount of water quality benefits. So ideally, you want to get in that 48 to 72 hour window. If your drawdown time is from your native soils exceeds that 72-hour window, then you would need to consider an under drain. Also, if you've got to include a liner because you've got groundwater issues or anything like that as well. The under drain is consisted not only of the lining at the bottom, but then you also want to have a clean out at the top, where the clean out in itself would be set at that water quality elevation in case at any time your under drain system becomes clogged, or you want to, or maybe even your in situ material over time becomes clogged. Okay. We also have, we want to make sure that we perch that under drain system into the section a little bit too, to give the opportunity, if there is any infiltration opportunities, to allow that water to be able to draw through the system before it immediately goes to the under drain system. And the under drain system ultimately too would be tied into the outlet structure as well. And like we saw on the other design sets, that outlet structure you need to design for your ultimate design storm. So typical local criteria will set the design storm. And so you want to look to your local criteria for that. But it's typically between a 25-year and 100-year design storm, where the top of the elevation is set to your water quality elevation. Okay. If you've got an under drain system, there are several layers to your soil media. The first one being your engineered media. Sheena went into detail of the components of an engineered media, but typically the depth of the media is anywhere from 2 to 4 feet, depending on your landscaping plan. So close coordination with your landscape architect to determine the appropriate depth for that, because if you're wanting to put in trees, then you're going to need to have a deeper section to be able to have adequate sustainability of that of those plantings. And then into the next layer would be the media barrier to inhibit material from the engineered media infiltrating into the bottom gravel layer. And this layer is included instead of a filter fabric that was used in the past, because fabrics are known to clog your system over time and can cause a maintenance issue. So it's better to do a graded system through here rather than putting in a filter fabric. And this is usually consists of a 4 to 6 inch layer of pea gravel, which is like 1/8 inch to 3/8 inch material. And then the bottom layer would just be the gravel layer. This is where the under drain would reside. And the gravel layer is comprised of a mix of a 1/2 inch to 1.5 inch washed stone. Really important during construction to make sure that that material is washed before it is installed, because you do not want to introduce any new fine particulates into your system from the get-go. This layer is typically around 12 inches thick, but it is really based on the size of your under drain. So if your under drain is only like 2 or 3 inches in diameter, then your gravel layer could be smaller. But typically the under drain is around 4 to 6 inches. So if you had like a 6-inch one and you need 6 inches of gravel above it, and then a little bit of room below it, like 2 inches below it, then you're going to need to have a thicker gravel layer. So completely dependent on the size of your system. And one of the last components would be just the vegetation selection in the area. You want to make sure that you use native or adaptive species that can handle up to 48 hours of inundation, but also can sustain long periods of drought, because we basically have, these are just to be fed with water when you have a storm event. So, I mean, if you're in the coastal area and the Houston area, you get this very often. But if you're in other areas of Texas, you're going to need to make sure that you select species that can have wet feet, but then also can go for long periods of time without with having dry conditions. Okay. We're going to step through a design example here of how to design a bioretention facility. And I see that we're kind of running close on time, so I'm probably going to step through this pretty quickly, but all the information will be posted here. All right, so the next one would be the engineered, or the first step would here is be selecting your engineered soil media depth. The minimum is going to be a minimum 2 feet to achieve the water quality goals, but it's also going to have to do with what you want to do with your landscaping plan. So it's important to coordinate with your landscape architect. And then the depth of the gravel, like we talked about, is around 12 inches, but also dependent on the size of your under drain. Next step. Okay, thank you. All right, so your storage depth ultimately is comprised of various layers in your site, and also the porosity of your engineered media and the gravel. So we provide a porosity values in the design set, but these definitely need to be verified with your suppliers. So make sure that you just don't run with those parameters, that you just, those are provided for guidance and for preliminary design, but definitely coordinate with your supplier to make sure that those values are appropriate. Okay. So we're going to step through a design example here of calculating your storage depth. So the first step would be would be the selection of your surface ponding depth. That is really up to the design of how deep you want your water to be. So typically it's anywhere from 9 inches to 18 inches. For this example, we use 1.5 feet. Okay, next. And the depth of the engineered media, depending on your site. Again, for this example, we use 4 feet. Okay. And the depth of the gravel layer of 1 foot. Okay. And so using the equivalent storage depth equation provided in the design set calculates a value of 3.1 feet for your equivalent storage depth. And this value is used to determine the area footprint for your bioretention cell. Go ahead. All right, something to note here is obviously in the design at any site, it is definitely an iterative process. So these are equations that are provided to get your feet going in the right direction, but obviously there's different knobs that you can twist depending on your site conditions. But for here, the preliminary footprint is developed by taking the water quality volume of the site divided by the equivalent storage depth that we calculated as in step 2. And the calculations for the water quality volume is provided in the implementation guide that Sheena stepped through. And that value is increased by 10% to account for sediment accumulation over time. So as an design example, we've got a, for this site, say we've got a contributing drainage area of 5 acres, a C value of 0.9, and a rainfall depth of 1.22 inches. It equates to a, and using the water quality volume equation provided in the implementation guide, that arrives in a water quality volume of 20,000 cubic feet. Please note, like Sheena mentioned earlier, we got a lot of different units with these equations. So like in this one, we've shown an area of 5 acres, but in the equation, you actually use cubic feet. So just kind of watch those units as you're stepping through the equations. And then for the next step, you would have a equivalent storage depth of 3.1 feet that you calculated in step 2, arriving at an area footprint of the permanent pool or of the water quality volume of just over 7,000 square feet. Okay. The next calculation is related to the drawdown time. We talked about that a lot, but you're basically wanting to make sure that it completely draws down in your desired drawdown time, but no greater than 72 hours. You want to make sure that also that the you want to just be able to infiltrate not only the top storage volume, but also take into account the filtration. And so it's really used in designing your underdrain system and determining the design rate for that. It's okay during preliminary design to start to determine if you're going to need an underdrain system, if for, say, cost estimating purposes, to use soil infiltration rates from the USDA website, but that is purely just for preliminary design. It's very critical during the actual design phase to do actual infiltration testing, because you want to make sure that that drawdown rate is around 1/2 inch per hour or greater. So let's go ahead and step through the calculations for an underdrain. So past from previous steps, we've got a surface ponding depth of 18 inches. Go ahead. And an infiltration rate, let's say for this example, we've got some really poor infiltration conditions, but we're wondering what that what that resulting drawdown time would be. So we have an infiltration rate of 0.2 inches per hour, which is less than the recommended of 1/2. And using the formula here in the design set relates to a drawdown time of 94 hours, which is greater than the 72. So that means typically that you would have to have an underdrain system for this design. However, there are other things that you can do that doesn't necessarily mean that you have to have an under drain. You also could do soil amendment to the in situ conditions to be able to increase the amount of water that soil can absorb. So say you amended your soil and you went from 0.2 inches up to 0.5 inches, and let's see what that ended up resulting in for the drawdown. That ended up resulting in a drawdown time of 40 hours, which is actually less than the 48 hours. And so then you have to think of, is that good enough, right? Are we close enough to the 48 hours? So then coordinating with their maintenance professional and then your regulators and the owner to understand if you maybe amended that soil too much or what you want to do, or if the 40 hours is close enough to the 48. And then the last step for the design of a bioretention cell is the outlet structure. And like we talked about before, the outlet structure is really just for design for your design storm. So typically around a 25-year to 100-year storm event, depends on the local requirements. You just want to make sure that you consider any type of trash rack that might be necessary, and consideration of making sure that the size doesn't cause a concern for the public. And one of the last elements in the design set is just additional considerations. So we've included in there permitting, construction, and maintenance recommendations, and the importance of making sure that you develop a customizable maintenance guide for your site. We want to make sure that you just don't use something off the shelf, but it's specific to your site in itself. And then coordinating that with the person who's maintaining the site owner, and any regulators that are controlling of things. We've also included site-specific construction recommendations based on lessons learned from designing and installing these type of BMPs. And so one example is the importance of installing the soil media immediately after following the excavation of the pond. Because if you're building immediately adjacent to, say, a roadway, if you leave that area open for extended amount of time, then your roadway materials are subject to the weather conditions and can really dry out and cause issues with your roadway conditions. So we really want to make sure that it is installed in a good sequencing and not left up to disturbing things. And then in the end, we've also provided some considerations for coastal areas, because this was built for the kind of Harvey impacted areas in the Houston area. All right, with that, I'll turn it up to Michael to close things out.
All right, thank you, Kim. Thank you, Friesen Nichols, for all that information. As I know, it might have seemed like it was a lot and we were rushing through it, but I think what's really important to remember, guys, is that this infrastructure toolkit is now available. Like, you guys have it. We share the link right here in the QR code. It will be in the chat as well, and we'll send that out via email. You can also get to it from our website. So take the time, look it over, and see how you can use it to improve your projects in your community. If you go to the next slide. Before we get to a short Q&A that we could answer some questions and be able to talk it out, I just want to, guys, remind you, here at Texas A&M AgriLife Extension, we are here to help all of our Texas communities move from planning to implementation to really help these projects along. And we can do that with providing education and outreach through workshops, presentations, and then online resources such as this. We do offer technical review and design support to help apply this toolkit more efficiently, and we can help connect practitioners with funding opportunities and networks to really get those projects from the planning stage to the implementation stage. So I want to thank you for your time. I'm going to pass it over to Christy. She's going to start off with a short little Q&A section.
Let me get my mic down. Okay, I did see one question in the chat. What are your thoughts on fabric or non-woven fabric on the bottom of infiltration systems, or even between the layers in the GI system? And we had an answer in the chat, but if one of our speakers wants to address that question, feel free.
Yeah, I just reiterated in the design example we show, yeah, we definitely don't want to include filter fabric because it's known for clogging. So we usually typically use a gradated system within the soil media. And we've shown an example of using a pea gravel for your media barrier between the soil media and your gravel layer.
Thank you. I do not see any more questions in the chat. I think there are some questions in the Q&A, so I will turn that over to Ayana.
Yes, there are a couple of questions here. It was during Shayna's portion. There's a question about, is there a statewide or regional standard for minimal infiltration rate for GI practices? And the continuation of that question is, Table 3 shows this. And also, is there a standard review check that requires verification for infiltration practices?
So I didn't see the original question, but yes, we do provide, typically the minimum infiltration rate is 1/2 inch per hour.
And the next question is, can you confirm that bioretention infiltration testing should be done at the bottom, at the interference in native and installed improved versus the surface of the BPM? I think you just answered that.
Yeah, so in the implementation guide, we provide a reference, I think, to the City of Austin's infiltration practice, and they step you through specifically that it definitely needs to go into the native soil. You have to consider your full depth of your infiltration practice to make sure you're able to infiltrate that depth. And it also provides the amount of holes you want to do based on the square footage of your control.
The next question is, RE infiltration rates and testings. Are there any videos or literature, even white papers for comparing/preparing urban GSI test? And more to that question is that they have a double ring infiltrometer, but based on Austin specs, it seems that the Precoloration test is preferred for most urban BPMs, medium parts, and treatment trains. They've hosted infiltration trainings and tried to find other videos, but it seems like a hiccup and still would like to measure pre and post construction.
I can't remember the professor's name, but there's a green infrastructure specialist out of Oklahoma State University that does a lot of these type of training and videos specific to this parameter. I can't remember his name off the top of my head right now, though. He's got his own YouTube channel with all these kind of instructional videos. You can probably find it pretty quickly, though.
It seems to be all the questions so far that I see in the Q&A portion.
Okay. Well, if it looks like we've gotten to all the questions, I don't see any more popping up. I will close this out for the day. Thank you to all of our speakers. There we go. Thank you for all of our speakers. Thank you for sharing your insight and for helping to prepare this resource for Texas communities. All of you guys who came to join us, the toolkit is available on the website as we gave you the link through the presentation. So feel free to go check it out, deep dive into the various design sets and share it with other folks who might be interested. The recording of this video will get sent out in the next week or so that you guys can all access that. It'll also be available on the website for future reference back to this recording. We'll get you guys copies of the slides, and all of that will come in an email within the next week or so. So again, thank you guys all for joining us. Thank you to our speakers, and have a great day.